Dimethylamine is a secondary amine that plays an important role in a wide range of chemical processes, medical developments, and industrial practices. This compound is particularly notable because it features two methyl groups that replace two of the hydrogen atoms typically bonded to a nitrogen atom. These substitutions significantly alter the physical and chemical behavior of the molecule, expanding its use across multiple disciplines. A full understanding of dimethylamine requires exploring its chemical behavior, environmental interactions, production techniques, health effects, and applications in modern industry. Amines are a class of nitrogen-based organic molecules derived from ammonia, where one or more hydrogen atoms are replaced by carbon-based groups. In the case of dimethylamine, it is considered a secondary amine, meaning that two of the hydrogen atoms attached to the nitrogen in ammonia are replaced by methyl groups. This substitution results in a structure composed of a nitrogen atom bonded to two methyl groups and one remaining hydrogen atom. The geometry of this molecule is trigonal pyramidal, with the nitrogen atom occupying the apex. The lone pair of electrons on the nitrogen contributes to the molecule's reactivity, ability to form bonds, and general chemical behavior. The replacement of two hydrogen atoms in ammonia with methyl groups brings about a number of changes in how dimethylamine behaves chemically. One of the most noticeable differences is an increase in basicity. Methyl groups tend to donate electrons toward the nitrogen atom, which raises the electron density and strengthens its ability to attract protons in chemical reactions. As a result, dimethylamine is more basic than ammonia. Another important characteristic is the presence of steric hindrance. The two methyl groups are relatively bulky, and their spatial orientation around the nitrogen atom makes it harder for other molecules to approach and react, especially in certain types of substitution reactions. In terms of hydrogen bonding, dimethylamine has only one hydrogen atom bonded to nitrogen, which limits its ability to form hydrogen bonds compared to primary amines. This has the effect of lowering the boiling and melting points and increasing the volatility of the compound. Chemically, dimethylamine is an effective base and a strong nucleophile. The lone electron pair on the nitrogen is readily available for bonding with electrophilic atoms, making it reactive in a variety of chemical environments. When introduced to an acidic medium, dimethylamine readily accepts a proton, forming a positively charged ion called dimethylammonium. This ability to undergo protonation is key to many industrial acid-base reactions. The increased electron density on the nitrogen also enhances its capacity to react with electrophilic compounds. For instance, in alkylation reactions, dimethylamine bonds with alkyl halides to form tertiary amines, which are valuable in agriculture and pharmaceuticals. In acylation reactions, it reacts with acid-derived compounds to create amides, useful in both organic chemistry and polymer development. Due to its chemical structure, dimethylamine is very soluble in water. It can form hydrogen bonds, though fewer than its simpler amine counterparts. Its boiling point is low, just above the freezing point of water, which makes it a gas at room temperature under typical atmospheric conditions. However, it is easily compressed into a liquid for storage and transport. There are several standard methods used to synthesize dimethylamine, and the method chosen usually depends on the required production volume. One of the most common techniques involves reacting methanol with ammonia in the presence of a catalyst such as zeolite or alumina. This process creates methylamine as an intermediate, which then reacts further to form dimethylamine along with water as a byproduct. Another laboratory-scale method involves reducing formaldehyde in the presence of ammonia, which also yields dimethylamine under the right conditions. The versatility of dimethylamine makes it indispensable in multiple industries. In agriculture, it is a key component in herbicides, pesticides, and fungicides. For example, one widely used herbicide is made from the dimethylamine salt of a compound designed to target broadleaf weeds, offering farmers a powerful tool for crop protection. In fungicides, dimethylamine improves the solubility and delivery of the active chemical agents, helping ensure even distribution across large planting areas. In the realm of polymer chemistry, dimethylamine contributes to the development of specialty materials such as ion exchange resins and modified polyacrylamides. These polymers are widely used in the treatment of water and in the manufacture of paper. When used in these contexts, dimethylamine influences both the structural properties of the polymer and its interaction with dissolved substances. In the pharmaceutical sector, dimethylamine is vital for the synthesis of many drugs. It acts as a precursor in the production of compounds that relieve allergies, reduce nasal congestion, and provide local anesthesia. Its role is especially prominent in nitrogen-based compounds, where its presence in drug molecules often enhances therapeutic activity. Dimethylamine also appears in compounds used to treat pain, manage high blood pressure, and address a wide variety of chronic conditions. Its reactivity makes it a flexible tool for chemists developing new therapeutic agents. Water treatment is another area where dimethylamine finds practical use. Salts derived from dimethylamine are used during the purification process, particularly in flocculation and coagulation steps. These processes help remove suspended solids from water by encouraging the particles to clump together, making them easier to filter out. The result is cleaner water suitable for industrial or municipal use. Because of its effectiveness and relative availability, dimethylamine has become a standard chemical in many large-scale water purification systems. Although dimethylamine is primarily produced in industrial settings, it also occurs naturally in small quantities. It can be detected in the environment as a result of organic decomposition, especially in marine ecosystems where plant and animal materials break down. In humans, it appears as a minor byproduct of protein metabolism, although it plays no active physiological role. In low concentrations, it is harmless, but larger doses can cause irritation or discomfort, especially when inhaled. From an environmental perspective, dimethylamine is relatively persistent. It does not degrade quickly and can linger in air, water, and soil for extended periods. This makes proper handling important, particularly in locations near bodies of water where marine organisms could be affected. Any accidental release or disposal must be managed carefully to avoid contamination. In terms of human health, dimethylamine is classified as an irritant. When inhaled in its gaseous form, it can affect the respiratory system, eyes, and skin. Exposure to high levels over long periods may result in more serious health issues, including damage to the mucous membranes. Because of these risks, workplace environments that involve handling dimethylamine must adhere to strict safety procedures. Protective equipment such as masks, gloves, and safety goggles is essential, and the area should be well ventilated to prevent gas accumulation. These measures help minimize the health hazards associated with routine handling of the compound. Looking toward the future, the role of dimethylamine may grow in both established and emerging sectors. With increased attention on sustainable practices and environmentally friendly chemistry, researchers are working to find new ways to produce dimethylamine using renewable resources rather than traditional fossil fuels. This would reduce its environmental impact and align production practices with broader global sustainability goals. At the same time, pharmaceutical science continues to explore new therapeutic avenues where nitrogen-based compounds like dimethylamine could be crucial. As new diseases emerge and treatments become more complex, the demand for versatile chemical building blocks such as dimethylamine is expected to increase. Dimethylamine is a compound of significant chemical, industrial, and environmental importance. Its molecular simplicity conceals a broad array of properties that allow it to function effectively in many settings. Whether serving as a reagent in chemical synthesis, an active agent in agricultural chemicals, a building block in polymer production, or a precursor to pharmaceuticals, its usefulness is widespread. Understanding how it behaves at the molecular level, recognizing the risks involved in its handling, and continuing to improve production and application methods will ensure that dimethylamine remains a valuable tool for science and industry. Its story is one of transformation and utility, built on the simple substitution of hydrogen atoms and extended into the complex networks of modern human enterprise.